Welcome back, everybody, to our next unit. We are going to cover Chapter 7 today with the range equation. So the range equation helps the machine to determine where to place reflectors. Now we know that when sound is sent into the body, it's going to interact with the reflectors. Some of it's going to come back and some of it is going to continue on. So remember, we have our transducer, that sound is sent out, hits a reflector, and goes back. Now we know that, again, some goes on, hits reflectors and heads back. Some will continue on, hits reflector and goes back. And then it's going to keep doing that. The machine is going to keep waiting for the single pulse that went out until it reaches the maximum depth that we have our machine set at. So maybe we're imaging down to 15 centimeters, maybe down to 20, whatever it might be. So that is one pulse that is sent out. Once all the echoes come back from this maximum depth, then the second pulse can be sent out. And again, it's going to hit things in return, go down, return some will keep going, and again, down to our maximum depth. And that's just going to keep happening for every single scan line in our picture, hundreds of them going across. And what the machine does then is figures out where are these reflectors, how deep are each of these reflectors that those echoes are coming back from. And it uses the range equation to calculate that. So the range equation, again, is used to calculate the time it takes for a pulse to enter the body and return, and then the depth is calculated based on that. So range equation, you'll hear a lot of times time of flight. So again, that's into the body and back, or go return time. So when we have a long time of flight or a long go return time, an increased time of flight or increased go return time, that means that the reflector is deeper in the body. So that makes them directly related. And that makes sense. If we look at our example here, the time it would take for sound to hit this reflector and go back is less than the time it would take to come down to this reflector and return back to the transducer. So as depth increases, the time of flight increases or gets longer. They're directly related. The other thing that the time of flight or go return time is calculated based off of is the speed of soft tissue. We know that ultrasound is a constant speed. We use that average speed in soft tissue, and that's 1540 meters per second. So we use that 1540 meters per second to calculate the echoes, because we know that the machine can't detect, oh, I'm traveling through bone right now, adjust for that. I'm traveling through fat right now, adjust for that. So we always use the 1540 meters per second. What you'll see much later in this series, or in this lecture, it's like chapter 21, I believe, we'll talk about artifacts. And so many of the artifacts that we see in our machine are based on the fact that the machine is assuming this 1540 meters per second, but we know that's not always true, because there are different speeds during the different types of soft tissue. But the speed of soft tissue is part of our calculation for the go return time. So here is our range equation. We have the depth in millimeters, so how many millimeters into the body is a structure. When we consider the constant soft tissue speed multiplied by the time it took to go in and come back, all of that divided by 2. So let's look at an example just using the range equation here. So we knew that our depth, again in millimeters, is equal to our speed in soft tissue. Remember, we're using all those kind of complementary units here, times the go return time in microseconds, and that's all divided by 2. So let's put in for examples, let's say it took 20 microseconds for the sound to go into the body and return. Remember, it's the go return time, in and back. Times that 20 microseconds, all divided by 2. 1.54 times 20 is about 30, so divide that by 2. We then know that our reflector is 15 millimeters into the body. So here's our transducer. 15 millimeters in, takes 20 microseconds for that sound to travel to the reflector and return back to the body. Now you might be looking at that equation and thinking, how am I going to multiply 1.54 times microseconds and then divide that by 2 in my head? Well, there is an awesome thing that we know about this equation. And that is the 13 microsecond rule. So if you can add multiples of 13 together, you are going to be golden, because the 13 microsecond rule tells us that for every 1 centimeter that a reflector is into the body is going to take 13 seconds for the sound to travel to that reflector and back to the ultrasound unit. So let's look at that again. We got our transducers here. Reflector at 1 centimeter, reflector at 2 centimeters, reflector at 3 centimeters. Clearly not to size here, but you get the idea. For that sound to travel to 1 centimeter and return all the way back to the transducer is going to equal 13 microseconds. For sound to come down and go back to 2 centimeters and all the way back, that's going to equal 26 microseconds. 3 centimeters down and all the way back, that's going to equal 39 microseconds. So I think you kind of get the idea. 4 centimeters in the back, 4 times 13, or 13 plus 13 plus 13 plus 13, we get 52 microseconds. Right? So that 13 microsecond rule is super helpful when we are talking about whole numbers and looking at the 13 microseconds. Now keep this in mind when you're taking your tests. Most of them are not going to be, what is it, 3.3 centimeters in? It's going to give you a 4 centimeter, it's going to give you a whole round number. So keep that in mind. If you can multiply the depth by 13 microseconds, you should be able to figure out the go return time, or by taking the go return time and dividing it by 13 microseconds, you should be able to then figure out the depth based on that. So you should be able to rearrange this equation to help you to understand how to calculate depth and then also how to calculate the go return time. Now something that I just want to point out as well, and Edelman spends a little bit of time on it in the book, is that the go return time and the depth are related, and they're also kind of related then to the total distance traveled of the sound. I'm going to go back to our whiteboard here. So here's our transducer traveling down to, let's say, 3 centimeters. So we know that this is going to take 39 microseconds, because 3 times 13 equals 39. So we know that the sound has to travel down to that 3 centimeters and back the 3 centimeters to the transducer. And so what you'll often hear is that the depth is 3 centimeters. Total travel, though, is 6 centimeters. 3 centimeters in, 3 centimeters back. All right. So we consider the 13 microsecond rule to be, again, 1 centimeter per 13 microseconds. To get the total distance traveled, you can then just double your depth. So I've got a few examples here that we can go through and use our new knowledge of the 13 microsecond rule to calculate. So our first example asks us, how deep is a reflector that took 13 microseconds go return time? Well, we just learned from our rule that 1 centimeter equals 13 microseconds. So you should know that one off the top of your head. That is an easy one to memorize. So a reflector that took 13 microseconds is 1 centimeter. We can take the go return time and divide it by 13. 13 divided by 13 equals 1. That gives us our 1 centimeter. The second example, how deep is a reflector that took 26 microseconds? Well, again, we can take 26 divided by 13, and that gives us 2 centimeters. So 2 centimeters in equals that 26 microseconds. Our next question is, time of flight is 39 microseconds. How far did the pulse travel? So when you get questions like that, that's asking the total distance. So we can take 39 divided by 13, and that tells us our depth is 3 centimeters. Okay, so remember 3 centimeters is 39 microseconds. But the question is asking the total distance traveled. So that's going to be into the 3 centimeters and back. So we just need to double this, and the total distance traveled is 6 centimeters. And then our last example asks, a reflector is 10 centimeters deep. What is the time of flight? So if our distance is 10 centimeters, we're going to then multiply that by 13 microseconds, and that's going to equal 130 microseconds to travel 10 centimeters. Just to expound on that question then, if you were told time of flight is 130 microseconds, what is the total distance traveled? Well, we know that the depth is 10 centimeters, but that total distance traveled requires us to multiply that by 2. So just another way to look at all of this. 10 centimeters takes 130 microseconds for the sound to go in and back to the transducer. That sound pulse then travels a total of 20 centimeters by going into the 10 centimeters and back 10 centimeters. So the 13 microsecond rule, or the range equation, is going to help us then to understand how PRP and depth are related. So if you think back to chapter 4 and think about what we learned about PRP, the pulse repetition period, remember that we could adjust it by changing the depth. And that was because that pulse needed to be sent out, travel to the maximum depth that we have our machine set at, all those echoes need to return, and then the next pulse can be sent out. So the 13 microsecond rule helps us to define how long that's actually going to take for the sound to leave the transducer and return back to it. So just going back to my example again, remember that pulse is sent out and it has to travel down to our max depth that we have, and it needs to come back. So all the time that it takes for it to come out and go back is our PRP, because remember that pulse is sent and that takes fractions of a second. Most of our time is that off time, waiting for the sound to come down and back up to the transducer. So remember when we were kind of graphing that out, we had our pulse and then that space, that off time, and then the pulse again. So that pulse is this, the off time is all of this listening time that we're waiting for. So it makes sense then that our 13 microsecond rule, or the range equation, helps to explain how long that time is going to take. And of course, there's a formula that goes along with it. Thankfully, this one isn't too different from what we just learned. So now that we know the 13 microsecond rule, we can determine how long PRP, or what PRP is going to equal, by taking the maximum depth that we have our machine set to and multiplying it by 13 microseconds. So let's take a look at an example here. So our example says, if our sonographer adjusts the imaging depth to 14 centimeters, what is the PRP? And then it asks, what is the PRP if it is 7 centimeters? So let's head to the whiteboard and take a look at these. So again, we're asking, we've got our transducer up here. And the first question is asking, we have the maximum imaging depth. So our sector is opened up all the way down to 14 centimeters. I have no idea if that's actually 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wow, that's pretty good. 14 centimeters. All right, so it's asking us what is the PRP for this example? And remember, we're sending that pulse out. That pulse has to travel all the way down to our 14 centimeters and back up before the next pulse can be sent. So we use our 13 microsecond rule. We take our maximum depth, multiply it by the 13 microseconds, and 14 by 13 equals 182 microseconds. So remember, on our graphing, we would have our pulse, our off time, and our pulse again. If this is what this pulse looked like, the time from here to here would be 182 microseconds. That is the PRP. Okay. So let's take a look at the other example then. It asked us, what is the PRP when our depth is set to 7 centimeters? So we've reduced our depth down to 7 centimeters. And now we want to know, what is the PRP of the pulse leaving, going down to 7 centimeters, and returning. So again, we can take 7, multiply that by our 13 microseconds. 7 times 13 then is 91 microseconds. So again, we can look at our graph. We've got our pulse, off time, pulse. So our PRP is, remember, the pulse duration plus the off time, and that's going to be 91 microseconds. So fun fact too, we saw that 7 centimeters is 91 microseconds, 14 centimeters equaled 182 microseconds. Notice when the depth was cut in half, the time of flight was also cut in half. So those are directly proportional as well. So showing that example, drawing it out, looking at how the numbers are related to one another, tells us again that pulse repetition period and depth are directly related. We know that when we increase the depth, the pulse repetition period also increases. So if PRP and depth were related, remember then that PRF and depth were related because PRP and PRF are also related. So the pulse repetition frequency is how many pulses can be sent out per second, knowing that we have to wait for those pulses to go all the way down to our maximum depth and then come back out. So remember, we have our transducer. We have our maximum depth set to whatever it may be. Oh, that's an awful looking sector. Anyway, pulse is sent out and comes back. And what PRF is asking, how many pulses can we send out and have them come back in 1 second? So PRF is related to depth because the more depth we have, the less pulses we can send out. Remember, it's much easier to go shallow. It's much quicker to do this versus coming all the way down to our maximum depth. So again, as the PRP increases or gets longer, that means that our PRF is going to decrease because we have to wait much longer for those pulses to be sent out and come back. So PRF and PRP, remember those are reciprocals and they're inversely related. So of course there's a formula then that goes along with PRF and the 13 microsecond rule. So remember that our 13 microsecond rule was derived from the range equation. And the range equation told us that for the depth in millimeters, it's going to be equal to the speed of sound in soft tissue multiplied by how long it took divided by 2. So if we kind of plug in some numbers just to help us understand this a little bit better, we can get to something that looks like this. And you'll see that these have been converted up into larger numbers. So now we're seeing that the constant speed of time is 154,000 centimeters per second. And if we plug in that it only took 1 second for the go return to time to happen and divide that by 2, we can see that a pulse can travel 7,000 or 77,000 centimeters in 1 second. So again, we're just taking that range equation, converting those numbers up, so we're just working with larger numbers than millimeters and microseconds. We're now using centimeters and seconds because that goes with our PRF. We just plugged a 1 in here just to see what would the time be, or what would the depth be if the go return time was 1 second. And when we plug that 1 second into our equation, we see that sound can travel 77,000 centimeters in 1 second. 1 second, that's really, really far. So what we find then is that PRF is going to be 77,000 centimeters per second divided by the imaging depth. So when we consider that 77,000 centimeters per second, when we consider that to be one event, and then we divide that by the imaging depth in centimeters, we end up getting our PRF. Let's look at an example here. So our first question asks us, what is the PRP and the PRF if the imaging depth is set to 14 centimeters? The second one then asks us, what is the PRP and PRF if the imaging depth is set to 7 centimeters? So let's go back to the whiteboard. And remember, we already figured out what PRP was based on these two numbers, right? We knew that it took 91 microseconds to travel to 7 centimeters, and it took 182 microseconds to travel to 14 centimeters. Remember, that was calculated by multiplying the depth times our 13 microseconds. So these are our PRPs. Okay. Now we're going to use the new formula that we just learned, that 77,000 divided by the depth is going to equal our PRF, or pulse repetition frequency. So if we take 77,000 and divide it by 7, our PRF then equals 11,000 hertz. Or it can travel to a depth of 7 centimeters 11,000 times. It can go down to 7 centimeters and back 11,000 times in 1 second. That's what that is saying. If we divide 77,000 by 14 centimeters, now our PRF equals 5,500, or that our pulse can travel to 14 centimeters and back to the transducer 5,500 times in 1 second. That is an amazing amount of traveling and speed that is happening. It is happening so quickly, it's very difficult for us to understand. But the big thing again is that we are looking at PRP is getting longer the more depth that we have, and our PRF is getting lower the more depth we have. Remember, 7 centimeters equaled 11,000, 14 centimeters equals 5,500 hertz. And both of those were for the PRF. So again, that tells us the more depth we have, the less pulses we can send out. They are inversely related. The more depth we have, or less depth we have, the more pulses we can send out. Inversely related. The more depth we have, the longer our PRP is. They are directly related. The less depth we have, the less our PRP is. Directly related. Now, fun fact, we can also, once we know either the PRF or the PRP, remember that they are reciprocals. So we can use the reciprocals of either of these numbers if you can't remember the two equations that we learned in this chapter. So for example, we know that our PRP is 182 microseconds, so we can take 1 divided by 182. We know that should equal our PRF, and that is going to equal 0.00549. So again, just to show you the math on the reciprocal, we can take 1 divided by 182 microseconds, which is the same as saying 1 divided by 0.000182 seconds. And remember, seconds is the unit that we need for PRF. So if we take 1 and divide that by that 0.00182 seconds, we get 5,494, which, if we round, equals our PRF as well. So remember, if you're going to use a reciprocal form and all you have is a PRP in microseconds, you have to convert that into seconds. You have to use your metric conversion to get to seconds. Divide the 1 by it and you get your 5,494. Now, as far as tests go with these numbers, you might not be able to divide 77,000 by the depth very easily in your head. So with that in mind, I would take some time to either memorize some of the common whole numbers that we would be using, or to get comfortable in doing some long division with on pen and paper. So you will have some practice doing this in your workbook, but like I said, if you want to just kind of get some practice in just converting numbers, I would maybe just make a chart, do PRPs and PRF, and maybe down the side I would just go 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. And you could just do that the whole way down, knowing that 1 centimeter is 13 microseconds, 26 microseconds, 39 microseconds, and then calculating the PRF along with it. The more practice you get with just using those formulas, the more you're going to understand it, the more you're going to see the relationship between how long it takes for images to be created, what that PRP is, how they're all related to one another. Now, for the most part, you should also be able to kind of estimate. 77,000 is very close to 80,000. So if you can kind of do whole numbers, say the question was, what is the PRF at 10 centimeters? And your options were okay, so 10 centimeters, first we know it's going to be somewhere in the thousands of hertz, right? So let's say your option was 7 hertz. Probably not the right answer. Say B was 77 hertz. Well, we're probably getting closer, but it's still not quite the right answer. Say C then was 7,700 hertz. And then D was 77,000 hertz. You can kind of look through these answers and should be able to estimate then that your correct answer is C. Now, dividing 77,000 by 10 is fairly easy. What is the PRF at 8 centimeters? And your options again were just kind of making these up as we go. 6 hertz, 5,000 hertz. C maybe is 10,000 hertz. And D, actually, let's pull that one out of there. We'll put in the actual number here. And D was 15,000 hertz. Again, we know that 77,000 divided by 8, it's close to 80,000 divided by 8. We should be able to pick a number that is near correct. So sometimes it's just a matter of estimating what your answer should be. You should be able to estimate getting to the correct answer based on what your other answers are. We know it's not these really low numbers. We know it's not that really high number. If you can do some quick math on a piece of paper, you should be able to calculate that down. All right. So again, no calculators needed on this. You should be able to estimate fairly well. And then if you use that chart as well, then you'll just be exposed to what the actual numbers are, and that'll help you just to, again, to see it all visually laid out for you. When you're making your cheat sheets for your final assignment, maybe including something like this on your cheat sheet would be helpful as well, especially if you don't think you can do the math quickly on a piece of paper. All right, and that is the end of the range equation. This is probably one of my favorite chapters just because I really like, it's a very concrete rule that for every 1 centimeter, again, this go return time is 13 microseconds. When we talk about total distance traveled, then we just multiply our depth by 2, so we double it because that's for in and going back to the transducer. So this is total travel. 1 centimeter is the total, or the reflector depth. And then know your PRP and PRF equations, knowing that PRP is the max imaging depth multiplied by that 13 microseconds, and that PRF is going to be 70,000 divided by the max imaging. And remember, those were all derived from the range equation. Okay, so lots of practice in your workbook. Do some practice on your own. Don't forget the questions in the book. There's lots of practice in there as well.